Hi everybody, I'm Zhang from USTC. I'm going to present our work, Depart, Replica Decoupling for Distributed Key-value Storage. In the era of big data, the data is growing exponentially and unstructured data is dominant. To deal with the challenge of data storage, key-value stores are widely used because of its flexible data model, high scalability, and simple interface. Examples of key-value stores include NavyDB, RocksDB, Cassandra, and so on. And most of key-value stores are based on the LSM-tree. It organizes data into multiple levels with an increasing capacity, and the data in each level are fully sorted and organized into fixed-size files called asset table. Note that when move data from a lower level to a higher level, data in both levels are required to be read out, merge sort, and then written back. This is called compaction. LSM-tree can transform random writes into sequential writes and keep each level fully sorted, so it supports efficient writes, scans, and high scalability. However, LSM-tree suffers from large write and read amplifications due to the multi-level log-structured design, which cause multi-level access during read and frequent compactions during write. On the other hand, distributed key-value stores are widely used for large-scale storage. For example, DynamoDB, Cassandra, ScalaDB, and so on. First, key-value pairs are partitioned to different nodes based on consistent hashing or key range. Then each node uses the LSM-tree to store all key-value pairs. Here we take Cassandra as an example. The key-value pairs are partitioned based on consistent hashing. There are 5 physical nodes with 2 virtual nodes each, so the hash ring contains 10 ranges. Each of the ranges is associated with the nearest virtual node in the clockwise direction and the corresponding physical node. So each node contains several ranges and stores them in the LSM-tree. Besides, replication is used in distributed key-value stores for fault tolerance. By distributing the replicas of each key-value pair across different nodes, we can divide the replicas into 2 types. The first is the primary copy. It is the main replica that is mapped to nodes by consistent hashing. The second is redundancy copies. They are the remaining replicas that are mapped to nodes by replication strategy. However, existing distributed key-value stores simply store all replicas together in a single LSM-tree for each node. We call this uniform indexing. It is easy to implement, but aggravates both write and read amplifications because there are more compactions and more data to search during write and read for uniform indexing. We also carried out experimental verification on Cassandra and TiKV. We deploy Cassandra and TiKV on a 5-node cluster with their default settings. We configure a client to write 300 GB kV to the cluster, then read 30 GB kV. Figures A and B show that for Cassandra. When increasing replicas from 1 to 3, the write amplification increased from 6 to 25, increased by about 4 times, and the read amplification increased from 7 to 34, increased by more than 4 times. We observe a similar trend for TiKV. Therefore, a larger replication factor implements higher read and write amplifications. In order to address the issue of uniform indexing in distributed key-value stores, our main idea is to decouple primary and redundant copies in the storage layer, so as to avoid the interaction between primary and redundant copies during read and writes. However, another key issue is how to manage primary and redundant copies separately after decoupling. One simple replica decoupling approach is to manage the key LSM-trees for key replicas derived from each key pair. For example, for Cassandra with triple replication, we use 3 LSM-trees in each node. one SM tree to store primary copies, the other to store redundant copies from two other nodes. However, mutable SM tree design has two limitations. First, since each SM tree has its own memory table, so the memory overhead amplifies by k times for k replicas. Besides, each SM tree incurs its own computation overhead for maintaining the fully sorted ordering in each level. Thus, the computation overhead is still significant. Our evaluation shows that when the client writes 200 GB under triple replication, mutable SM tree only reduces the total computation size of Cassandra by 21%. Therefore, we propose to part a distributed KV store that builds on Cassandra to realize replica decoupling by separating the storage management of primary and redundant copies. For primary copies, we use SM tree to store, so as to achieve efficient writes, reads, and scans. For redundant copies, we design the tuner log to manage them, so as to achieve faster writes and provide tunable performance. Besides, the part has several key design points, including replica differentiation, tuner log with tunable ordering, and payload recovery. To realize the idea in the part, we have to address several key challenges. First, how to differentiate the primary and redundant copies with limited overhead. We propose a lightweight replica differentiation scheme. This figure shows the workflow. When node N receives one of the replicas of the K pair, it performs the hash computation on the K and determines the node to which the K is hashed according to the consistent hashing. If the resulting node is current node N itself, then we refer to the replica as primary copy. Otherwise, the replica is the redundant copy. The differentiation scheme is based on simple hash computation, so it is low overhead. Second, how to manage redundant copies after decoupling. We propose a tuner log with tunable ordering to enable faster writes. Each node writes all redundant copies flushed from the immutable memory table to an append-earning global log. All redundant copies are grouped in units of segments and appended to the header of global log as sequential batched writes. To enable fine-grained management and faster recovery for redundant copies, a background thread continuously splits the global log into multiple local logs, each of which keep only the redundant copies, whose corresponding primary copies are stored in the same node. For example, local log I stores redundant copies whose primary copies reside in node I. Besides, since each node stores several ranges according to consistent hashing, we divide each local log into multiple range groups, each of which corresponds to a range in the hash ring. Note that different range groups have no overlaps in case, so they can be managed independently. The range grouping can improve the GC efficiency and recovery, because both of them only need to read the corresponding group, avoid scanning the all local log. In addition, each group contains several sorted runs. Note that the K pairs within sorted run are fully sorted, but unsorted across sorted runs. Therefore, we can adjust the number of sorted runs within the group to balance the read and write performance. If we keep fewer sorted runs within the group, then we achieve a high ordering for the tuner log that can ensure better read performance. If we keep more sorted runs within the group, then we achieve a low ordering that can ensure better write performance. Finally, how to adjust the ordering of the tuner log. Considering that the ordering determines the trade-off between the read and write performance, a small number of sorted runs in a range group favors the read performance, but it incurs a large merge sort overhead that degrades the write performance. So we can set different degrees of ordering for the tuner log based on the performance requirements. To support a setting with a high read consistent level under read-dominant workloads, we should set a high degree of ordering with fewer sorted runs in the group to benefit reads. Otherwise, we should set a low degree of ordering with more sorted runs in the group to benefit writes. The third challenge is how to perform recovery efficiently after replica decoupling. We propose a parallel recovery scheme that explores the benefit of decoupling the primary and redundant copies in the storage layer. When building trees to detect lost data, we use two threads to read primary from the LSM tree and redundant copies from the two-layer log in parallel. Besides, when repairing multiple branches, we also use two threads to read primary and redundant copies in parallel from the serving nodes, then issue parallel writes for the primary and redundant copies in the failed node. We run all experiments in a local cluster that has 6 nodes. The table shows the server configuration. We use YSV tool to generate workloads. By default, we focus on 1 kilobyte queue pairs and generate requests based on the ref distribution. We deploy 3 replicas and set both write consistent level and read consistent level to 1. We compare our depart with Cassandra and multiple LSM-tree design. We first compare the performance of Cassandra, multiple LSM, and depart in different KV operations, including writes, reads, scans, and updates. Figures show the throughput. First, depart improves the overall performance over Cassandra in all cases. Second, multiple LSM notably improves the read performance over Cassandra, but only show marginal improvements on writes. The reason is that multiple LSM still trigger frequent complications that degrade the write performance. We also evaluate the performance under different consistency configurations. For strong consistency, we consider 3 different configurations for write consistent level and read consistent level under triple replication. We can see that depart consistently improves all the throughput over Cassandra. Depart also improves the throughput of writes and updates over multiple LSM. However, the read performance gains of depart over Cassandra become smaller, and depart's read performance is worse than multiple LSM for read consistent level greater than 1. In this case, each read request needs to access at least 2 replicas successfully, so the redundant copy in the two-layer log must be searched. As the redundant copy in the two-layer log are not fully sorted, the performance is slower than reading the primary copy in the LSM tree. Note that depart still achieves faster rates than Cassandra, as it searches for less data. Also, multiple LSM keeps the redundant copy being fully sorted in each level, so it achieves a higher read performance than depart. We also evaluate the recovery performance on recovering a failed node. We consider different write size, then create one node and remove all its data. Finally, perform recovery. The results show that depart reduced the recovery time of Cassandra by 38 to 54%, and depart mainly reduced the time costs of building trees and receive and write data by nearly half of Cassandra, by reading and writing the primary and redundant copy in parallel. We also evaluate the write and read performance under different settings of the ordering degree S, so as to show how depart can balance the read and write performance gains for the redundant copies. If the value of S is equal to 1, the two-layer log reduces to a 2-level LSM tree, so it achieves the highest read throughput as the queue pairs are fully sorted, but the write throughput is the least due to the frequent merge sorts. As we increase S from 1 to a sufficiently large value, the ordering of the two-layer log is relaxed, and hence the merge sort overhead becomes smaller. So the write throughput increases, but the read throughput decreases. To conclude, we propose depart, a distributed key-value storage with replica decoupling, to enable high performance and reliability. The part contains several key designs. Please refer to the paper for detailed results and analysis. We open source the code in our project website. Thanks for your attention.